Okay, so I came across this problem. This problem seems to be troubling lots of students lately. So this problem is pretty straightforward if you are familiar with how to write half equations. That's from AS. If you know how to write half equations from Unit 2 of AS, you should be fine. So let's read this problem. So in this experiment, this experiment is being carried out to check the oxidation number of chromium in chromium to ethanoate. So this is chromium to ethanoate. So what's happening is they gave us the mass of chromium to ethanoate they took and the moles of chromium to ethanoate they took. So that they dissolved it in 25 cm cube of sulfuric acid, and then the solution was made up to 250 cm cube. Okay. And then 25 cm cube portion of this dilute solution was titrated against 0.00750 mole per dm cube potassium manganate 7. So that is KMnO4. Okay. Calculate the volume of potassium manganate needed to oxidize the chromium ions present in each 25 single portions to the +6 oxidation state. Calculate the volume of potassium manganate 7 needed to oxidize chromium 2 ions present in each 25 single portions to the +6 oxidation state. Okay. So basically this mole was dissolved in 250 cm cube, right? This moles of chromium to ethanoate. So we're taking only 25 cm cube out of it. So we're basically taking 1/10 of this. Okay. Okay, that's pretty straightforward. So before we begin, it's better to write what's happening here. So chromium 2 plus is being oxidized to chromium +6. So if you remember from AS, so this is chromium 2 plus. If you oxidize it, this guy will lose electrons and become chromium 3 plus. And if you have chromium 3 plus and you're oxidizing it to chromium doesn't exist as Cr6 plus alone. So basically what it's going to exist as is a dichromate ion. So that looks like this, Cr2O7, 2 minus. So here the oxidation number of chromium is +6. So we need to balance the chromium. So I need 2 Cr3 pluses. And the way we do this is from EAS, is we have to balance the oxygen. So we have 7 oxygens on this side. So in order to balance the oxygen, you just add water. So I have 7 oxygens here, so I'll add 7 water. Now I'd be like, oh wait, now I have hydrogen here. There are no hydrogens there. So yeah, I need to balance the hydrogen there. So I have 14 hydrogens here, and I'm gonna have 14 H plus ions there. So in this problem, if you see that they have added sulfuric acid, dilute sulfuric acid. The reason is you need these H pluses for these reactions to happen. So this is what you commonly hear as acidified dichromate, potassium dichromate. So this is why you need to acidify it. Okay, it's not over yet. So if we look on the left-hand side, let's see the total charge, right? The total charge here is +3 times 2. So the total charge on the left-hand side is +6. And the total charge on the right-hand side is +14 minus 2. So that is +12. So now we see that the charges are not balanced. So what we do now is we have to add electrons to balance the charge. So I'll add 6 electrons on this side. So that would make this +6, right? Now this guy becomes +6. So this is a proper half equation. So if I'm coming from +2 all the way to +6, I need to balance this as well. So I need 2 Cr2 plus, 2 Cr3 plus, and 2 E minus. So now what's going to happen is the overall equation for this half equation, the 2 Cr3 pluses are going to cancel. So now I'm going to add them up. So 2 Cr2 plus, I'm going to add all the left-hand sides together. So I do not have any Cr3 plus on the left-hand side anymore. So I have 7 water molecules. That is becoming Cr2O72 minus and 14H plus. And notice the electrons on the right hand side are going to add up. So I'm going to have 80 minus. So that's that. So this is 1/2 equation of chromium 2 plus becoming chromium 6 plus. So we're halfway through. And then the question says that the dichromate 6 is basically oxidizing it. So the manganate 6 has been reduced to +2 oxidation state. So as the manganate ion is oxidizing the dichromate, it has to get reduced. So now we're going to write the half equation for the manganate. So for the manganate, the potassium manganate, potassium is the spectator ion, so we're not going to worry about that. So this is the manganate MnO4 minus. So if you do not know how this is manganate 7, the way you would find this is, let's say the oxidation number of manganate is X, and the oxidation number of oxygen here, the oxidation number of oxygen other than when it's a peroxide or superoxide is always going to be -2 when it's bonded to somebody. If it's alone, then it's going to be 0. So in this case, each oxygen has an oxidation number of -2. So you have 4 of those. So -2 times 4. And the overall charge is -1. So that is -1. So I can figure out that X is equal to +7. So manganate here, so manganese here has an oxidation state of +7. So that's how you do it. I'm going to get rid of this now. Okay, so this guy is being reduced to Mn2 plus. So again, I need to balance the oxygens. I have 4 oxygens here, so I'm going to add 4 water molecules on the right hand side. And there are 8 hydrogens, so I'm going to add 8 H plus ions. So there you go. Now we balance the charges. So on the left hand side, I have +7. On the right hand side, I have +2. So what I'm going to do is I have to add 5 electrons on the left hand side. I need to move the arrow a little bit to make room for the electron. Okay. So let me move the arrow to the right. So I'll add 5E minus. 5E minus here. Nice. So now the charge is balanced too. This half equation is complete. Now I'm going to write the overall equation. The overall equation is when my manganate is reacting with my chromium and oxidizing the chromium, and itself is getting reduced. So in an overall equation, we cannot have electrons, right? So if we just add the left-hand sides here and the right-hand sides here now, then I'm going to have electrons, right? So we cannot do that. So in order to cancel the electrons, I need to multiply this equation by, we can multiply this. So I have 5 electrons here and I have 8 electrons here. So they're on the opposite side, so they're going to cancel out as long as they're of the equal number. So I need to find a common number, multiple of them. So 20 is 1, right? So if I multiply 8 by 2.5, if I multiply this equation by 2.5, then I'll end up having 20 electrons. And if I multiply this equation by 4, then I'll end up having 20 electrons. So I know that. So once I do that, so I can write it down, I guess. Let me write it again. So 2 times 2.5, so I have now 5 Cr2 plus 7 times 2.5, this is 17.5 water. Then I have 2.5 dichromate. Then I have 14 times 2.5, that is 35 H plus. And I have 20 electrons on the right hand side. And for the next one, I multiply everything by 4. So I have 4 MnO4 minus. I have 32 H plus. I have 20 E minus. I'm just multiplying all of them by 4, right? So I hope you are getting this. And then I have 4Mn2 plus, and I have 16 water. Okay, now we can go on and get rid of stuff. Okay, now we can write the overall equation. Okay. So the left hand sides and right hand sides are going to cancel out. So I have 20 electrons on the left hand side here, and I have 20 electrons on the right hand side here, so they're going to cancel out. I can simplify it even further. I have 32H plus here and 35H plus here, so they will cancel out. And I'll have 3H plus here. The waters are going to cancel out. 16 water, 17.5 water, so I'd have 1.5 water here. So basically, they are the ones that are going to cancel out. So now I will write an overall equation. So overall equation is basically all the left-hand sides, arrow on all the right-hand sides. So I have 5 Cr2 plus, 4 MnO4 minus, and then I have this water on the left-hand side. That is 1.5 water. That's going to react to produce 2.5 dichromate, 4 Mn2 plus, and 3 H plus. So yeah, I didn't miss anything. Okay, nice. So this is the overall equation. So now the crucial bit here is to realize that 5 moles of Cr2 plus reacts with 4 moles of MnO4 minus. So that is the mole ratio, right? That's what we need. That is the mole ratio. So we did all of this work to figure out the mole ratio. So in this problem, we've seen that I have taken this many moles, 2.66 times 10 to the power minus 3 moles of chromium ethanoate, and which was made up to 250 cm cube. So in this 250 cm cube, I have 2.66 times 10 to the power minus 3 moles of chromium ethanoate. But I didn't take all of it to react with KMnO4, right? I just took 25 cm cube of that, right? 25 cm cube of that portion was taken. So I've basically taken 1/10 of this. So now I'll figure out the moles of chromium ethanoate taken, right? So the moles, let me get another color. Okay. So moles of chromium ethanoate in 25 cm cube is going to be the total moles, 2.66 times 10 to the power minus 3 mole divided by 10, right? So how do I know it's 10? Because it's 250 divided by 25. So that's 10. So it is 1/10. So this is going to be 2.66 times 10 to the power minus 4 moles. So we're not done yet. So this is the mole of chromium ethanoate, right? So chromium 2 ethanoate. So if we look at chromium 2 ethanoate, if you look at the formula, right? So I have 2 moles of chromium 2 plus for each mole of chromium ethanoate, right? I have 2 chromiums in 1 molecule of chromium ethanoate. So basically, now this is the moles of chromium ethanoate, but this is not the moles of chromium though. So moles of chromium 2 plus. Moles of chromium 2 plus in 25 cm cube portion is gonna be 2.66 times 10 to the power minus 4 times 2. So that is 5.32 times 10 to the power minus 4 moles of chromium 2 plus, right? So this is the mole of chromium 2 plus that's reacting here. So this is that. So according to the mole ratio, it has to be 4 by 5. So the moles of MnO4 needed. So mole ratio, according to the mole ratio. So moles of manganate needed to react with that bit is gonna be the moles of chromium, which is 5.32 times 10 to the power minus 4, times the molar ratio. So 5 moles react with 4 moles of manganate. So this much would be 4 times 5. So that is so that has to be 4.26 times 10 to the power minus 4. Let me recheck the calculation again, just to be sure. Yeah, so this is the moles of MnO4 you need, MnO4 minus you need. This is the moles of MnO4 minus you need to oxidize 5.32 times 10 to the power minus 4 moles of Cr2 plus into Cr6 plus. So in the problem, we're given the concentration of the manganate, which is 0.00750. So I know the moles of manganate that's needed. I know the concentration. So the concentration is 0.00750. So the concentration of MnO4 minus is 0.00750 mole per dm cube. This is MnO4 minus. So I know the moles of MnO4 minus, I know the concentration, I can figure out the volume. So the volume, so moles equals to concentration times volume, you know this bit. So volume would be mole by concentration. The mole was 4.26 times 10 to the power minus 4 mole divided by 0.00750 mole per dm cube. The moles are going to cancel out. The denominator of the denominator is going to go up. So what we have here is okay, so what we have here is 0.0568 dm cube of manganese solution. In cm cube, this is going to be times 1000. So that is 56.8 cm cube. So don't worry about the acid because it's technically, it's just to acidify it. It's not reacting with the MnO4 in this case. So we're not going to worry about that. And the last part asks that comment on your answer and suggest how the experiment could be improved. So if you look at the titer value, it's over 50 cm cube, and we know that a burette is, the capacity of a burette is 50 cm cube, right? So this is way more than 50 cm cubes, and the problem you're going to have is you have to refill the burette before finishing one titration. So that's a nuisance. You don't want that. This is good because a higher volume is going to give you a low percentage uncertainty, but you don't also, but a very low volume is also bad. You don't want 10 cm cube or something. An ideal volume should be, an ideal titer should be 25 cm cube maybe. So in order to reduce the volume, what you can do is increase the concentration of the MnO4 minus. So increase the concentration of the MnO4 minus so the titer volume goes down a bit and it's easier to do the titration.